So I plan to share some of our research on this topic. Because I know we are from the different backgrounds, some from computer science, some from non-CS areas. So I may not go into a very deep in technical part. I mainly focus on the research problem we work on and some high-level idea. But some topic I may choose go into a little bit deeper. If you don't get the whole thing, don't need worry. If you, I think it's more for CS people, especially if you are not from CS background. Maybe some part may be difficult for you. But everything I talk is you can find in some papers. So I also, in the end, I gave the list of the papers. Also, some part of the talk, you can also find some papers. So if you would like to know more, you can refer to those papers. Also, during the tutorial, anytime if you have a question, please feel free to stop me to ask questions. So I first give an overview about the research done in my group. So we mainly focus on the data-driven research, but we mainly focus on the geospatial plus X data. So here, X can be a different type of data. For example, it could be a text, it could be a temporal, it could be an image, video. The data can be from different sources, so we list some here. For this kind of data, one problem we work on is building a data system to manage, to querying, to analyzing this kind of the data. So one thing we did is if the data is come as a stream, we also call it a geospatial data stream. For example, if you consider Twitter, then the people keep tweeting something. There's a lot of tweets actually they have geolocation, especially if you tweet from your mobile phone. Then we can consider this as spatial data streams. And to handle this kind of data streams, we may need build some data management system or data system. Then for this kind of the system, we need to solve the some research problem. One typical problem we need to solve is how, if we build a distributed system to handle streams, we need to distribute both the data and the workload. Workload could be the query or some analysis requirement over the different computers. Then one thing we need to solve is how to balance different computers to get the workload balance. So it's one typical research problem we need to solve when we develop a distributed system. Then the other system we are trying to build is we want to build a system to manage the spatial plus X data. For example, the X could be a text, could be some other attributes. Then basically we need to build an index to build a query processing algorithms to design storage, different things we need to work on. Then the other topic we work on is we also work on the machine learning for spatial database. I think in on Friday, I will give a talk in ADC conference. I will talk this topic, machine learning for database or spatial database. So this part is more for data management or building a data system. Then the other topic I work on is for this kind of data, we also want to perform some more advanced data analytics or data mining. So based on the different geospatial properties, we divide them into three types of data: point data, trajectory data, and region data. Then for each type of data, we may have different problems and different applications. For example, for the point, we may point in one example is like the point of interest data. Then for this kind of data, we like if you use a Google map, you may want to search some point of interest. So it's a search problem. Later on, I focus more on this part. So then I also do something on the trajectory data. the trajectory could be from the vehicles, could be from the animals, from the humans. Then for the trajectory, we also need to consider what is the efficient way or effective way to represent a trajectory. Then we can compute the trajectory similarity. For example, during the COVID, if we know the trajectory of a person with a COVID, then we may want to find those similar trajectories. So then we need to compute the similarity between trajectories. Then for the region, later on we also choose some topic from the region 1. Then for these 3 types of the data, so previously what we try to do is for each type of data we may have some application or some task. Then we design some solution. But recently with foundation model, large language model, then there's a shift with paradigm of doing research. So we also doing something like a spatial foundation model for representing geospatial entities. Currently, my team mainly work on these 3 topics. So today, I will cover the this one, spatial foundation model for geospatial entity representation. Then for the ADC talk, I will focus on this topic. So this outline for today's 2 sessions. I first choose 3 specific research problems on the point geospatial entities. Then I will introduce the problem. Then the next session, I will talk about the shift of the research paradigm. So it's a bit different from the first 3 problems I choose here. So we first look at if the geospatial point geospatial entities, for example, point of interest. Then for this, I also gave an overview about the research we did on this one. So our goal actually was to construct some knowledge graph for those point of interest data. We try to work on some specific research problem for this topic. One thing is we try to integrate the different geospatial data. For example, we may have the point interest data. Then we also have the tweets. We may also have photos from the different social medias. But then we want to integrate them based on the geolocation. For example, if they are all about a particular point of interest, for example, all about this building, then we want to find out to integrate them together. Then the other problem is to build the knowledge graph. So one major thing is we need to find out the relationship between the entities. So we consider 2 kinds of the entities. One is semantic entity, semantic relationship. For example, if the 2 point of interest are competitive to each other or they are complementary to each other. For example, if we have 2 restaurants next to each other on a street, so likely they are competitive to each other. But if we have a restaurant and maybe we have a museum, if they are next to each other, then they are maybe complementary to each other. So we want to find this kind of the relationship. Then we also consider some other relationship. For example, if the 2 geospatial entities, they are from the 2 different data sources. For example, one maybe from the Google Maps, the other one maybe say from Yelp. But they are maybe the same point of interest. Then we want to find out if they are the same one. So this task is called entity resolution. We also try to do some extracting a location from the social media data. For example, if someone sent a tweet, then the tweet may mention some location. Then we want to identify or extract such a location information. Then we also do some geospatial information retrieval, or we also call a spatial keyword query. Why we have two names? The main reason is researchers from the different community, they all work on this topic. Then they give them different names. If people from the information retrieval, they may call geospatial information retrieval. But for the people from the database community, they call spatial keyword query. Then we also do some recommendation for point of interest data and also the POI data exploration. Today I select three problems and we'll give more details about them. So we first look at the first one, geospatial information retrieval. We first give a little bit more about the geotextual data. We also call it spatial textual data. So for this kind of data, they have the geolocation, like the latitude, longitude. But we also have some text content. So it's one typical example is points of interest. But also some web pages, actually, they also have the location information. So for this kind of data, we may want to do queries on this kind of data. We also call it geographic information retrieval. So for this query, like what you use in Google Maps, you may have some location, and we also have some query keywords. So it's some application could be the geographic search engine, location-based services, and some targeting advertisement. So here is an example from Yelp. Like a user issue a query as a point, then give some query keywords. Then the Yelp may return a list of the point of interest. This point of interest should be closer to the query location, and they are relevant to the query keywords. Then for this type of requirement or application, the researcher, they have developed a different kind of the queries to meet this kind of the user need. So there's three basic type of the queries. So next we use some example to try to explain these three type of queries. So basically is we have two parts. One part is the location part. The other one is the keyword part. So we want to find something closer to the query location. And also the text part should be relevant to the query keywords. Actually, these two more from the two different communities. So for the keywords part is more from the information retrieval community. But for the location, the distance part is more from the database community. So it's why earlier on I say we have the two different names for the same thing. Also then for these two types of the information, we can handle them differently. Then we have a different type of the spatial keyword queries. So we first look at the first one, the Boolean range query. So why we call it a Boolean range query? We first introduce what is the semantics for such a query. So here we have some point interest like the O1, O2, O3 are point interest. Then for the query here, we have two queries here. For this query, we have the keywords. Then we also have a query region, so shown in this circle. Then for this semantics for this query, they want to find those POIs located within this region. Then also a match with query keywords. So this we call it a Boolean range query. So the Boolean actually is for the keyword part. So we treat keywords as a Boolean query. So for this one, like if we have the cafe and sale, so this point interest contain both query keywords. So it's a Boolean conjunction query. Then for the range part, it corresponds to the spatial part. So we need the point interest located in this range. So this one type of the basic query. So then the second type of query we call it the Boolean keying query. So this semantics is a bit different. So the Boolean is also correspond to the keyword part. Then for the keying is for the distance part. Also the query is a bit different. So here we have the Q1. Here we have the Q1 is a query location here. Then we have this keyword. Then what we want to find is those object, they should contain this keyword T. Then we rank those object containing the keyword T based on the distance to the query location. Then here we can see this one is most close to this query location, also contain the keyword T. Then this 2 is rank 2 result. So if we say, if you use Google Maps, if you use this kind of query as a query engine, then they may return this first one, this second one. So this is second type of query. Then we want to introduce another type of query. For this query, like we have this query location, we have some keyword. Then for this query, the semantics is a bit different. So it rank the object based on both distance and text relevance. Based on these two aspects, then we will return this top one, top 2 result. Then the ranking function is given in the top. So for the ranking function, you can see we consider the distance to the query location. And we also consider the text relevance to the queries. So the text relevance, actually we can compute using any information retrieval model to compute the text relevance. It's basically how relevant is query keywords to the text description of each object. Then the distance we can simply use like Euclidean distance. So in the literature, there's a lot of work on how to handle these different type of the spatial keyword query efficiently. They build a different index. But however, we found almost no work. They study the effectiveness of the different type of the query, like which query can return a more accurate result. So this is not clear from the literature. So why there's almost no such work? The main reason actually is a lack of the ground truth query. So the reason here is for this type of query, you can imagine, so it's a very personal. Like the different user, they may issue the query at different location. Then they have the different preference. Then for the normal search engine query without location, then it's still possible, like given a query keyword. Then if some information retrieval algorithm returns some web pages, then you still can get some user to do the annotation to get the ground truth. But for this kind of query, we have both location and the keyword. It's very difficult to get people to do the annotation to generate a ground truth. In our work, fortunately, we get two real-life query log data from a company. So the company, they provide the location-based services. It's a bit like the Yelp. Then they have the query log. They also know what the user clicked. So we can use this as ground truth data. So we know the query. We also know what is a ground truth. Then we can use this to evaluate effectiveness of the different queries. So this is what we did. So in our work, we have these two data sets. Then we want to evaluate the different type of query to see how good they are. Then I next introduce the main result we get from this experimental study. So the first finding we find is, so for this result, this part is more for the three type of query here. So this is one type of query. So this corresponds to one type of query. This also corresponds to one type of query. The first finding I want to introduce here is that we found the keyword information is quite important in the spatial keyword query. So why we say that? So if we consider these two versions, the TKQ is we consider both distance and the keyword as a ranking query. So then the 0 it means we only consider the distance. Then the TKQ1 means we only consider the text relevance. Then if you compare these two, this is better. So here is we have the three metrics to. So these three metrics are widely used in evaluating the ranking effectiveness. They also used by search engine to evaluate how good they are. And then for this three type of query, we consider we find the third type of query they are better than the first two. So the third type of this TKQ, they consider both distance and keyword as a ranking query. Then another major finding I want to talk here is we find for this TKQ query, rely on a hyperparameter alpha. So this alpha is the trade-off between this distance and the text relevance. Then you can see if we vary the alpha value from the 0 to 1, then we can see the result are very different. So it's highly affected by the hyperparameter alpha. However, we find if we can see for this one is when we set alpha as 0.1 for all the query, it gets the best result compared to the other values. But we also consider another case. For this case is for each query, we try the different alpha value from 0, 0.1, 0.2, 0.3 until 1. Then we choose a best one for this particular query. If we do this for every query, then we can see we can get this last row here. Then can get even better result. But the thing is, how can you get the best alpha value for each query? So this is not possible actually. It's not possible to do that in practice. So in practice, it's possible like you just set a 0.1, then that's okay. But it's not possible if we say we try every parameter, then we choose the best one. But however, this one is say if we can, this experimental result tells us if we can design a query-dependent. If we can design a solution, we can set a query-dependent weight value for each query. Then we can get better result. So it's one open problem is how to design such a solution. Then the other open problem we want to consider in this work is for the information retrieval, also with large language model, there's a lot of research. They use deep relevance model, or they also call a dense retrieval to compute the text similarity for search engine. So we also consider if that we also help with spatial keyword query. So it's two open problem we want to consider in this work. Then for what we want to do is we find out for the TKQ query, it get better results. So it rank object based on these two aspects, distance and text relevance. But there's a hyperparameter alpha here. So we want to design a solution to find out a query-dependent alpha value for each query automatically. Then the other thing is for the text retrieval part, we want to use this relevance model based on the deep learning techniques. So these are two things we want to do in this research. Then we also do some data analysis. We find the optimal setting for this alpha is related to both query keywords and query location. Then we develop a deep relevance model with query-dependent weight learning. We call this model a DRW model in our work. So next, I give some high-level idea how we design solution for these two open problems. The first one is we want to design text relevance model based on the deep learning or based on in information retrieval. They also call it dense retrieval. Basically, it's for query keyword. You can learn the representation for each query keyword. So there's a lot of work from the information retrieval about that. So like the very famous one, like the early days, we had the word to vec, then we have the bird, and we have many other techniques. Like the ChatGPT, they will also can give you the embedding for each word. So embedding is just like a vector. For each word, then you can get a vector for each word. Then for the text description for the PUI, for each word, you can also get an embedding for each word. Then we need to compute the similarity between the query word and the text description. So what we did is for each query keyword here, we compute the relevance with the word in the PUI. Then the PUI may contain many words. There may be too many of them. Then to make faster, then we just use top K query word. So basically, top K word from the PUI text. So basically, for each query word, we find the top K most similar words from the PUI text. So we do this for every query word. Then after that, so this corresponds to the for each query word, we find the top K most similar word from the PUI text. Then we need have some way to aggregate all of them to get the final ranking score. Then we use some attention mechanism to aggregate them. So the attention is widely used in large language model. So basically, we find some way to aggregate all these similarity value. Then we get the final similarity value. So that's the idea for this part. So how we design deep relevance model to compute the similarity between the query and the PUI text. Then the other part we want to solve is we want to get a query-dependent weight. So then this part is given the query keywords, also given the query location. We want to use some deep neural network to find the best value for the hyperparameter alpha. Then after we have this one, then we can use this query-dependent alpha value to aggregate the text relevance and the distance relevance. So the text relevance is computed by the method in the last slide. So this is the main idea for our proposed solution. Then we also conduct experiments to compare with different baseline. So this type of baseline is more like those models from the information retrieval community. They only consider the text relevance. They don't consider the distance. There are also some work they consider both text relevance and distance. So this last is our own method. Then we do some experiments on these two data sets, Beijing and Shanghai data set. Then we can see this baseline method. So this DRW is our proposed method. For those methods, the baseline method, the best one is TKQ method. Then our proposed method can very often can get a 30% better result in terms of the accuracy measured by the different metrics here. So it's a very significant improvement. Then we also do some experiments. Say if we don't learn the query dependent hyperparameter alpha, we just set the best one. We find out for this experiment the best one is 0.5. Then we only get this result. But if we can set this query dependent alpha value, we can get a much better result. So this also shows the query dependent hyperparameter learning is useful.
Just to be sure, the three baselines are the three metrics are all accuracy metrics, right?
Yeah, all accuracy metrics.
And do you focus at all at the efficiency, like time efficiency?
We also did some experiments on efficiency, but I didn't include here. But yeah, for the experiments here, I introduced is all about accuracy.
And how would you say your method compares time-wise?
Time-wise, so for this, the dense retrieval-based method, so the efficiency is definitely much worse than those traditional information retrieval model like a BM25. So for this, dense retrieval is much slower. We have to design some other ways to speed up. It's a very good question. So for this kind of the problem, definitely both efficiency and accuracy are very important.
And also, did you, so obviously you said that there isn't a way to determine which parameter for the alpha for like from 0 to 1, but would you have, say, a recommendation or like an intuition on how to choose this metric? Because 0, 1 was the best for the experiment, but I assume that it's like for a different data set or
yes, definitely. Yeah, it's a very good question. So the alpha, if you just set a fixed value, then I think what you could do is you may have to have some validation data to tune the parameter to find a good one. Actually, we also find if we say use a different way to compute the text relevance score, like in the previous experiments, we find like if we set the alpha value at 0.1, it get better result. But if we use the deep relevance model or the dense retrieval to compute the text relevance part, then we find out if we use a 0.5, we get a better result actually. So there's another very good way to set this parameter. You have to use a validation set. But in our solution, actually, we design a way to automatically to set this alpha value for each query. Like after we train the model here, then given the query keywords and given the location, then this model can tell you a good alpha value for this particular query.
Perfect. And then the last thing, so basically your approach is algorithmic, right? Mm-hmm. Do you also like consider the way you're storing the data, you're indexing the data, or this is something that you fix and you're working on basically the algorithm and comparing it to the baselines?
It's a very good question. Yes, for this work, we just focus on the accuracy. We don't consider the index, how to store the data yet. But that's definitely very important. As I mentioned, actually in the literature, quite some work, they build an index for this kind of data to speed up the query processing. But for this one, we just focus on the accuracy. Yeah. Welcome. Any more questions? Okay, then we move to the next topic about the PUI recommendation. So the PUI recommendation, the problem setting is like this one. So we have a set of the point of interest. Then we also have a set of the users. So you can maybe consider like the Facebook Place or the Yelp. They all fit with this setting. Then for users, we already know some PUIs they visited before. Then for the PUI recommendation is I want to recommend some new PUI the user are likely to visit. This PUI recommendation help user to explore new places and also help the company or business to get new users or new customers. So for this PUI recommendation problem is has some properties are different from the other recommendation tasks. So I know some of you may do, I'm not sure if some of you do research on recommendation. So if you, normally like the recommendation is quite useful in product recommendation or the movie recommendation, those kind of things. But compared to those recommendations, so here we have the two differences. One is for the pure recommendation, the data could be very sparse. So so what does the sparsity means? So given the recommendation task, basically you can consider like the user item matrix. Then if a user already purchased some product or they visit some POI, then this corresponding entry in the matrix will have some value. But for the other entry, we don't have the value. Then this, if you have a lot of entries, you have value, then the matrix is relatively dense. But however, if we don't have a lot of value, then it's very sparse. Then for a recommendation, like for the movie recommendation, those evaluation data set, the sparsity is like this one. So this means like the 1% of the entry they have a historical rating. But for the PUI recommendation, those popular data we use only 0.1, so it's much sparse. So it's one challenge. The other one is for the PUI recommendation, they may have a rich context. So here we give two contexts. One is geospatial influence. So this like the human, they are more likely to visit a nearby PUI. So if we do some statistics from the data we have, like if we, for the two adjacent places user visit, we compute the distance and we draw this figure. So we find the majority of the two adjacent visits are very close to each other. You can see this x is the distance of the two adjacent visits. Then the y-axis is probability value. You can see if the distance is close, then it has a high probability. But if say more than 10 kilometers, then the probability is quite small. So this data analysis shows the people tend to visit a nearby location. Then the other important context is time information. So this for PUI recommendation, if we say we do the recommendation in the morning, or if we do the recommendation at night, then very likely we need to recommend different things to the customer. But for the other recommendation, like the book recommendation in Amazon or the product recommendation, you may not have these properties. Then in our work, we try to extend the basic version of the PUI recommendation problem. So one problem we consider is context-aware PUI recommendation. So for this context, it could be the time. Then it could be the current location. So for example, we may have the current location is the office. Then we have the time is Friday evening. Then we make some recommendations. So likely we may recommend some restaurant or bar. So this means the recommendation is highly affected by time and current location. So we actually we work on this quite early, around 2013. We published first paper. We call the title is a time-aware PUI recommendation. So it's the first paper. They consider the time as a context for PUI recommendation. Then we also try to propose some other type of the POI recommendation problem to meet the different need. For example, for sometimes if we know the user requirement, for example, if we have this requirement, this person I want to find a restaurant to have pizza. Then this requirement is have a restaurant to have pizza is a requirement. Then we can also have more information. If we know the recommendation, it could be for a group. If the user say want to find a restaurant with his friend Bob, then this is also called a group recommendation. We can also say give the time. Then it will be also time aware. So this you can say if your user requirement is like this one, then when you do a recommendation, you need to take into these factors into consideration. Then another problem we propose in our previous work is we can also recommend customers or visitors for a POI. For example, if a POI restaurant, then maybe we can try to recommend some potential customers for this restaurant. So this like called a user recommendation. So in our previous work, we propose this different recommendation problem for POI recommendation. So this figure give more illustration for this POI recommendation problem. So the POI recommendation is like a model as input data as a matrix. So we have the user, then we have the location. Then if you say you know the user visits a location 6 times, then for the question mark is we don't know. We need to make a recommendation if the user will be interested in this location or not. Then if we have the time aware POI recommendation, then say for this maybe for the morning, for afternoon, for the night. Then you can say if we want to make the recommendation to be time aware, then we need to divide this matrix into the 3 sub-matrix. Then with this, we may have more question mark. And then it means data, input data become more sparse. Then it also means this problem become more challenging if we consider time. Next several slides is our early work, as I mentioned, is in 2013. Is the first paper considering time for POI recommendation. In that paper, we propose some very simple method. It's based on the user-based CF or item-based CF. But nowadays, all the recent work is based on the deep neural network to do the recommendation. But say 10 years ago, we used a very simple method. But it doesn't mean the recent deep learning-based method always better than this very simple method. According to some experimental study, they find if you tune the parameter for this very simple method, they on quite some benchmark data set, they can even perform better than those deep learning-based method. So here is we have the user, we have the item. Then for this, we have the 1 or 0. So 1 means the user visited this location before. Then for the 0, actually is a question mark. We want to know if the user is interested in the location or not. Then for the user-based CF, the basic idea is if given a target user U, we want to make recommendation for the target user U. What we want to do is we want to find those users who are similar to the target user. We want to use their data to do the recommendation. So this is also called a collaborative filtering method. Then how we can find those similar user to the target user? We need to have some similarity measure. So here we can use cosine similarity, but you can also use other similarity measure like Pearson correlation to compute the similarity between user. So here, if we use a cosine similarity, you can compute for the user U and V, for any two users, you can compute the cosine similarity to measure the similarity. Then after you get a similarity, then you may choose, say, a top K, maybe a top 10 most similar user. Then you use their historical data to make recommendation. So this recommendation score can be computed by this one. So here, for example, you may just take a top 10 most similar user. Then for you use their rating on the location. If say we want to recommend on this location, if you want to compute the recommendation score, you can use the other users' rating for this location to compute the recommendation score for this target user. So that's a high-level idea. In our work, we want to consider the time into the recommendation. So we modify this similarity measure between the two users. We consider the time. Basically, we divide the matrix in based on the time. Then for each time, if we say we have 3 timestamp, then for each timestamp, we compute the similarity, then we sum up them. So basically, we just modify this formula to incorporate the time factors. So I think the details for the formula are not important. So this is how we incorporate the time. Then the other thing for PUI recommendation is we need to incorporate the spatial influence. So based on the data analysis, we found out that people are more willing to visit a nearby PUIs. So when we design the recommendation model, we want to take into this into consideration. So these are just some design of the recommendation model. Basically, what we want to achieve is if we know the user visit some location, then those nearby location will have a higher recommendation score. So this is what we want to achieve from this model. Then the last task I choose is we want to infer some geospatial relationship from the geospatial database. So given a geospatial database like this one, it may contain the latitude, longitude for each point interest and address and some other information. So this is the input. Then the output we want to get is a knowledge graph for geospatial entity. Then for this knowledge graph, particularly we design several relationships we want to focus on. So one is we want to find out if a PUI is within another PUI. So for this one, because from the input, we only have the coordinates, but we don't have the polygon for the geospatial entity. So we need to infer this if one PUI is a part of the other PUI. Then the other relationship is because the data made from the different sources, then we want to know if they are the same one. It's also called entity resolution. The other relationship is if, say, there's a car park near a museum, then this car park very likely serves a museum. So it's also a type of relationship we want to discover from the data. Then for this task, there's some challenges. So one thing is that the data may be from the different source, and but the location information may be inaccurate. So this one is say if we have two data sources, one is from Yelp, the other one is from OpenStreetMap. Then actually all these PUI issue within this shopping mall. But however, if we just use coordinates, we find a lot of them are not in the shopping mall. This the main reason actually because the coordinates are not accurate. Then we design some models. Basically, is given the two locations, we want to predict the relationship. Then we also conduct some experiments. We compare with different baseline. Then we find out the so this is our propose a solution. Then we conduct the experiments on 4 data sets. We find out we are better than the baseline. So here is a summary for this part. So for this part, I choose 3 tasks. The first one is geospatial information retrieval. The second task is recommendation. The last one is relation extraction. Actually, for each task, we try to design deep learning model to learn the representation. So for the first one, actually we learn the representation for query. We also learn the representation for the geospatial entity. Then we will compute the relevance score between the query and the geospatial entity. So this one is we need to have some training data to learn the representation. Then the model is just designed for this particular task. Then for the second one, actually, essentially, we also learn the representation. For this one, we also need to have some training data to learn the representation. We learn the representation for user. We also learn the representation for geospatial entity or PUI. Then after that, we compute we match them to compute the recommendation score. Still, we have some supervised model to do this. Then the representation is just for this task. Then for the last one, the relation extraction. Then what we do is actually it's also learn the representation. It's for 2 entities. We learn the representation. Then based on the representation, then we want to infer the relationship. Basically, we also have some training data. Then we design some deep learning model to learn the representation. Then this representation is just for this particular task. But however, with the foundation model or the large language model, we find this paradigm shift for doing research for this kind of the task. Actually, before the foundation model, there's already some call it self-supervised learning. What they do is from the data they learn some representation without using the label data. Then for this representation, then can be served for the different downstream tasks. Then it can be served for the geospatial information retrieval recommendation and many other tasks. But of course, from here, after we have this representation, when we serve the downstream task, we also need fine-tune the model with label data. So the afternoon talk, I will focus on this paradigm to say how we can use self-supervised learning to learn the representation. Then we can serve for the different downstream tasks.
Thank you for a great presentation. My question regarding to the AI applications and spatial enabled data. I want to know that how do you think what is the most challenges work in maybe modeling the spatial relationship, such as topological relationship in AI application and AI machine learning methods? Just for elaborating that, we have lots of geospatial information that contain location, but it's not just the location. We have some other relationship with some entities like intersects, like containments, and some other relationship in geospatial context. I just wanted to know that how we can actually leverage this information into the AI applications, like the one that you mentioned about spatial relationship that you modeled with a knowledge graph.
Let me try to understand your question. Your question is like if we have this different geospatial relationship, how can we use them for AI application?
As a training data set. Yeah. I just wanted to know what is the biggest challenges and how we can actually encounter these challenges.
Maybe you can further explain your question.
Yes. Imagine we have spatial training data sets containing location and also relationship between the location, such as these 2 points of interest in the same polygon. And also we have not only the distances, the other relationship between them, such as culture, social economics, or something like that. I just wondering that how we can use and actually integrate this information to have integrated spatial training data sets to train the model and actually have better results from that model.
Yeah, this question is a bit too broad.
I think that he mentioned, you know, that we have a different kind of topological relationship, such as disjoint, joint, overlap, included, excluded. I think that he wants to know how this kind of relationship would be modeled in an AI algorithm, such as, for example, if we use neural networks, how we can model this one as a neuron.
For another example, we have lots of spatial temporal algorithms that used for time series and spatial informations. I'm just wondering that is it possible to leverage the relationship, not actually exact location or spatial information to the AI application or not?
Yeah, definitely it's possible, but the AI application is too broad. Maybe let me, if you give me a more specific application.
For example, let's talk about generative AI. We want to make spatial training data sets because, as you know, there are lots of challenges to collect the spatial training data sets, not like as other data sets. And how we can have spatially enabled generative AI application to create spatial training data sets using not location, the other relationships. It might be another question, but I just wanted to actually elaborate that we might need some other criteria, not only the location and the distance, to have better representation of the actual reality. I'm just wondering that how we can actually leverage these other criteria, for example, the relationship of the point of interest to the to the AI-based models.
I think if we just see the application I give here, like the first one or maybe the second one, geo information retrieval or recommendation. I think if you have the location, if we talk about the AI model, if we in this context like the language model, if without the location, like when you learn the representation of the word, like the bird, then you can model the context is more the in the same sentence. If those word near to this center word, they are the context. But if we have the geospatial information and location information, I think this location information can provide additional dimension for the context information. With this, you can learn the better representation. So then you can get better model, can support the application like the GRR or recommendation better. So without the context, you can just use a sentence. Those words are the context for this word. But with geolocation, like if we see two nearby documents, they are very close to each other, or the two POI very next to each other, then there can be also the context. So you have more context to learn the representation. So if you consider a bird, then you can. I'm not sure if you know a bird. It's a very famous model to learn the representation for text. But if you have the location, you can somehow you can incorporate the location to enrich the bird model.
Yes, thank you. I've just asked a question because the distance might different definitions in different geographical locations. Because when we say that I'm near you, it's not actually practical. It's 1 meter, 10 meter, or that. Because different social economics or other actually geographic information are related to the proximity. And so I'm just thinking that it might not have definitely actually a unique definition for distance, and we might have actually another consideration case by case. Yes.
Yeah, definitely. I think the location is a different dimension. One is how do you measure the distance. It could be a Euclidean distance. You could consider if you have the root network distance. So I have many other ways to measure the distance. Then this is one dimension, how to measure the distance. The other one is when you use a distance for some application, actually it's very often it's quite you need to personalize this location if it's for the user context. That's why we say we need to design a user query-dependent hyperparameter alpha, because different people may have the different perception on the distance. Like some people may feel 1 kilometer is very far. Some people may consider it's not far. So yeah, you have to consider this into the applications.
Thank you.
Yeah.
My question is somehow related to the previous question, but for a different application. I'm working with process data, and it's like that I have both the effect of time, because in each minute, the value of the target variable is dependent to the previous, like in previous minute and other previous recordings. So it's a temporal effect. And at the same time is affected with other input features, right? It's not like weather prediction or so. It's not pure temporal and not just the effect of other inputs. So I need to consider both the time effect and the effect of input features. I'm just wondering which method, based on your experience, work better. For example, machine learnings are great in considering just the effect of input on the output, and not that much powerful for considering the temporal effect. And time series methods can consider just the trend, not the effect of inputs. For example, based on what I studied, LSTM models were good, but yeah, just wanted to know which methods do you recommend for this kind of application?
So it means for your application, you have the time dimension, but you have other dimension. So
Yes.
then you need to consider all these different dimensions.
Yes,
What would be
I have different inputs, several inputs, and one target variable, but they are all time stamps. Yeah, so I have both the effect of time and the effect of different inputs on the target variable.
Okay.
Yeah.
Yeah, I think there's different models to handle this problem. Like for the currently, the deep learning model, they can definitely solve this problem. Like the transformer or the early on the RN, I think they can also model the different dimensions, time dimension. Also the other features they can also incorporate. Like the large language model, actually, it's all based on the transformer architecture. Yeah, I think that would be quite a suitable model so it's if you use those new model, I think it's those transformer or the RN model, they can be used. But the other possibility, maybe like you just model them separately, then you have some attention as a way to learn some attention to aggregate the different factors. That's another possible way, I think.
Yeah, okay, thank you.
You're welcome.